Welcome to the presentation for our paper, Neural Architecture Search of Deep Priors Towards Continual Learning Without Catastrophic Interference. Prevalent literature in deep continual learning typically focuses on alleviating catastrophic interference. That is, when we continuously train on multiple tasks in sequence, representations are greedily overwritten by the optimization process. In our paper, we instead ask ourselves the central question: what if we didn't need to infer a deep encoder's parameters and thus didn't have to worry about catastrophic interference altogether? To gain some intuition, take for instance the task of Visvanathan classification. If we train a linear classifier on the raw input data, we can obtain roughly a 41% test accuracy. However, if we first compute a 2-convolutional layer encoder with entirely random weights, and then proceed to train the linear classifier on top, the accuracy rises significantly to, in this case, 60%. Full encoder training further raises this performance, but quite crucially, we see that there are substantial benefits when the structure of the network resonates with the structure of the data. In our work, we follow 4 formulated hypotheses, which investigate whether we can push obtained accuracies of such deep priors to the degree of fully trained counterparts, and subsequently leverage the merits for continual learning. Specifically, we formulate a deep prior neural architecture search, DPNAS, in order to find suitable encoder candidates with random weights. Central to our work, we first conjecture that there exist deep priors, which we can discover through modern architecture search techniques, that lead to a classification task solution to the same degree of a fully trained architecture. For this purpose, in below DPNAS illustration, we first sample a deep encoder architecture, including relevant variables such as the number of layers, convolutional filters, poolings, or skip connections. In contrast to full training, we now use sampled random weights to transform the dataset. Based on this randomly projected embedding, we then evaluate the quality of the sampled deep prior by training a linear classifier on top. The resulting accuracy and network topology are stored in a replay buffer, which serves the purpose of updating a reinforcement-based Q-learning agent. Over time, this agent learns to find suitable deep priors. Crucially, we emphasize that the Q agent and linear classifier are the only components that require training. This makes the search orders of magnitude more computationally efficient than conventional NAS. To see how this works in practice, we show a DP NAS on Fashion MNIST. Each point on the x-axis represents one sampled architecture. The y-axis shows the rolling average reward, corresponding to the classifier's validation accuracy. In addition to this moving average, each point is color-coded to represent the individual architecture's accuracy. We can see that it is initially very hard to find a good deep prior. However, towards the end of the search, the agent has learned to sample deep priors that yield classification accuracies that rival those of fully trained networks. In order to highlight that this observation is a consequence of the architecture, we investigate 2 additional hypotheses. First, we demonstrate that redrawing new sets of random weights for deep priors does not result in substantial accuracy change. Bad deep priors thus remain bad, and good priors remain good, irrespectively of the precisely sampled weights. Second, we also show that full training of deep priors would always increase the final accuracy. However, for the best deep priors that already capture the structure and the architecture, there is negligible benefit from additional encoder training. We conclude our paper with an investigation of the utility of deep priors for continual learning. In a final hypothesis, we posit that if classes in a dataset originate from the same distribution, finding a deep prior on a subset should span prospective application to the remainder of classes. We investigate this in 2 continual learning setups, multi-head disjoint classifiers and a single-head classifier. In multi-head experiments, we corroborate our final hypothesis by showing that the deep prior seems to be generic, and no catastrophic interference is observable with encoder weights remaining random. For single-head investigation, we now also need to prevent catastrophic interference in this single classification layer. However, in contrast to previous literature works, not in our random encoder. Using a small core set of data exemplars, we can observe how this performs remarkably similar to more complex and tailored continual learning approaches. Please visit our paper for a detailed discussion and various experiments. In conclusion, we believe that our work can serve as a basis for development of alternate solutions, and we will be grateful if you read our paper for full details, discussions, limitations, and prospects.